A Chinese cargo aircraft just completed the world's first flight powered by a megawatt-class liquid hydrogen turboprop engine. 16 minutes in the air, 36 kilometers covered at an altitude of 300 meters above Zhuzhou Airport. Let me tell you what that actually means in plain English. The aviation industry has spent 30 years and billions of dollars concluding that hydrogen propulsion was physically possible but commercially impossible. Too heavy, too cold, too expensive, and too dependent on infrastructure that did not exist. This flight did not just challenge that conclusion, it challenged every assumption the conclusion was built on. If you want to understand how a program that the Western aerospace establishment dismissed as a decade behind schedule just landed a working aircraft, and what that means for every hydrogen aviation roadmap currently sitting on a ministry desk, subscribe and turn on the notification bell. Because the aircraft is not the story, the system that flew it is. For decades, the aerospace engineering community operated under a consensus so well supported by data that questioning it felt less like scientific dissent and more like wishful thinking. Hydrogen, the argument went, was a beautiful fuel on paper and a practical catastrophe in the air. The physics were not in dispute. Hydrogen carries roughly 2.5 times more energy per kilogram than conventional jet fuel, around 120 megajoules per kilogram versus 43 for kerosene. By weight, it wins. But aviation does not run on weight alone, it runs on volume. And by volume, the picture inverts completely. Liquid hydrogen stores approximately 8 megajoules per liter. Jet fuel stores around 34. To carry the same energy as a full kerosene tank, a hydrogen aircraft needs a fuel vessel roughly 4 times larger. Picture taking the fuel tanks on a commercial narrowbody, stripping out everything else in the fuselage, and filling that entire space with insulated cryogenic storage, and still not matching the range. That is not a design challenge. That is a structural redefinition of what an aircraft is. Then there is the temperature problem. Liquid hydrogen must be stored at negative 253 degrees Celsius. 2 degrees above absolute zero, the theoretical floor of all thermal energy. Achieving that temperature requires active refrigeration systems with their own mass, their own power draw, and their own failure modes. The insulation surrounding the tank must be thick enough to prevent heat bleed from the ambient airframe, which on a hot day on a sun-exposed tarmac is sitting at positive 40 degrees or higher. That is a thermal gradient of nearly 300 degrees across a wall measured in centimeters. Materials science has no off-the-shelf answer for that boundary condition at aviation weight targets. Boeing studied hydrogen propulsion seriously in the early 2000s and concluded the airframe integration challenges were not solvable within a commercially viable weight budget. Airbus ran its own internal hydrogen feasibility studies across multiple program cycles and repeatedly deferred the timeline. The International Civil Aviation Organization, in its 2019 environmental report, classified hydrogen propulsion as a technology requiring fundamental infrastructure and certification development before any realistic commercial deployment, and placed that deployment horizon firmly beyond 2040. These were not conservative institutions hedging their bets. These were the organizations that built the certified infrastructure for every commercial aircraft flying today. When they said hydrogen was not ready, they were not speculating. They were reading their own engineering data. The cost dimension made the physics problem worse. Green hydrogen, produced via electrolysis powered by renewable energy, the only variant that delivers on the zero emission promise, was trading in 2020 at between $8 and $12 per kilogram in the most optimistic production scenarios. Jet fuel, even at elevated prices, runs below $1 per kilogram on an energy equivalent basis. That gap does not close with incremental efficiency improvement. It requires a wholesale restructuring of the hydrogen production and distribution economy. No single aircraft program could build that alone. But the wall was never just physical. It was institutional. The certification pathway for a hydrogen-powered commercial aircraft did not exist. The CAAC in China, the FAA in the United States, and EASA in Europe had no approved framework for cryogenic fuel systems in passenger-carrying aircraft. Building one would require years of regulatory development, parallel to the engineering work with no guarantee that the two timelines would converge. The aerospace consensus was not pessimistic. It was honest about the scale of the problem, and that honesty is exactly what made what happened next so difficult for the establishment to process. The program that produced that flight did not appear overnight. In 2021, the Aero Engine Corporation of China, AECC, the state-owned enterprise responsible for every major propulsion program in Chinese aviation, formally announced a hydrogen combustion engine development initiative targeting megawatt-class turboprop output. The stated goal was not a laboratory demonstrator. It was a flight-ready propulsion system capable of integration with existing cargo airframe platforms. The Western aerospace press noted the announcement and moved on. The consensus reaction, where it existed at all, was measured skepticism. Hydrogen combustion in a turboprop cycle was a known engineering pathway, but the timeline AECC was implying, from program launch to first flight in under 5 years, was not considered credible by institutions that had spent decades mapping the same territory and stopped short of it. The objections were specific. Hydrogen combustion in a gas turbine environment produces nitrogen oxide emissions at high temperatures, complicating the zero-emission narrative. Liquid hydrogen fuel systems require ground infrastructure, cryogenic storage tanks, specialized refueling equipment, boil-off management protocols that no commercial airport outside a handful of research facilities possessed. And the certification pathway for a hydrogen-burning engine under China's CAAC airworthiness framework, let alone any international equivalent, was essentially unwritten. These were not abstract concerns. They were the same concerns that had caused every Western hydrogen propulsion program to stall at the feasibility stage. They said the same thing about China's high-speed rail network in 2003. We all know how that ended. What the skeptics did not account for was the structure of the program underneath the announcement. AECC did not approach hydrogen propulsion as an isolated engine development problem. It treated it as a systems integration challenge from the first design review. The AEP 100 engine, the designation that would eventually power the Zhuzhou flight, was developed in parallel with a liquid hydrogen fuel delivery architecture, a cryogenic ground handling protocol, and an airframe integration study conducted with Air White Whale, the cargo drone manufacturer that would eventually supply the test platform. Northwestern Polytechnical University and Beihang University, two of China's premier aerospace engineering institutions, contributed research teams to the thermal management and combustion stability workstreams. This was not one program. It was 4 programs running simultaneously toward a single flight demonstration. The skeptics were focused on the fuel. What they missed was the propulsion architecture being built around it. The first engineering problem AECC had to solve was one that sounds deceptively simple until you think about it for 30 seconds. A turboprop engine running on kerosene receives fuel at roughly ambient temperature, pumped from a wing tank, atomized at the injector, ignited in the combustion chamber. The thermal management problem at the fuel delivery stage is modest. Now replace that kerosene with liquid hydrogen stored at negative 253 degrees Celsius and route it through the same fuel delivery architecture. What happens at the injector is not combustion. It is a phase change event. Liquid hydrogen flashing to gas faster than the injection system can control, producing pressure spikes that no turbine combustion chamber is designed to absorb. Think of it as trying to pour liquid nitrogen directly onto a cast iron skillet at full heat. The surface does not just boil the liquid, it superheats it explosively, and the pressure wave goes somewhere. In an engine, that somewhere is the turbine blades. The solution AECC developed for the AEP 100 was a staged thermal preconditioning system built into the fuel delivery line upstream of the combustion chamber. Liquid hydrogen leaving the cryogenic tank is routed through a heat exchanger that uses waste heat from the engine exhaust cycle to raise the fuel temperature in a controlled gradient, not to ambient, but to a stable supercritical state where the hydrogen behaves as a high-density gas rather than a phase transition liability. By the time the fuel reaches the injector, it is no longer a cryogenic liquid threatening to flash. It is a controlled, high-pressure gas stream with predictable combustion characteristics. The ground test data AECC reported prior to the Zhuzhou flight showed combustion chamber pressure stability within 2% across the full power range, a figure that matches the stability envelope of mature kerosene turboprop systems that have been in service for decades. The thermal gradient managed across the preconditioning system exceeded 270 degrees Celsius in under a meter of fuel line. Named materials in the heat exchanger wall included high-temperature nickel superalloy on the exhaust side and cryogenic-rated stainless steel on the hydrogen side, with an insulating interface layer to control the transfer rate precisely. That number, 2% pressure variance, is not a promising early result. That is a production-ready combustion stability figure. But solving the thermal delivery problem created a second problem that the program had known was coming since the first design review. The preconditioning system added mass. And in hydrogen propulsion, mass is the variable that the entire efficiency argument depends on. Every gram added to the fuel system of a hydrogen aircraft carries a cost that does not exist in the same way for kerosene. Because hydrogen's volumetric energy density is already 4 times lower than jet fuel, the aircraft is already carrying a heavier, larger fuel system just to match the range of its conventional equivalent. Add a thermal preconditioning system with heat exchangers, insulated line segments, and pressure regulation hardware, and the weight penalty compounds. The engineers at AECC ran the numbers after the preconditioning architecture was finalized and arrived at a mass figure for the complete fuel delivery system that threatened to erase the efficiency advantage of hydrogen combustion entirely. The system that solved the phase transition problem had introduced a weight problem that the airframe could not simply absorb. The conventional response to a cryogenic tank weight problem is material substitution. Swap steel for aluminum alloy, reduce wall thickness to the minimum structural margin, accept the weight saving and move on. AECC did not do that. What the program's engineers proposed instead was a structural inversion that sounds, on first reading, like it should introduce more problems than it solves. Instead of treating the cryogenic fuel tank as a separate pressure vessel installed inside the airframe structure, the standard approach, which requires both the tank and the surrounding airframe to carry independent structural loads, they proposed integrating the tank wall itself as a primary load-bearing airframe element. The tank would not sit inside the structure. The tank would be the structure. The material that makes this possible is carbon fiber reinforced polymer, CFRP, manufactured in a filament wound configuration that allows the fiber orientation to be tuned simultaneously for cryogenic pressure containment and bending load resistance. The same wall that holds liquid hydrogen at negative 253 degrees Celsius also carries the wing root bending moment in flight. There is no redundant structural layer. There is no separate pressure vessel. The two functions occupy the same material in the same geometry. Testing conducted by AECC and reported prior to the Zhuzhou flight demonstrated that the integrated CFRP tank airframe assembly achieved a pressure rating of 3.5 bars at cryogenic temperature with zero structural deformation beyond the designed elastic range, while delivering a mass saving of approximately 23% compared to a conventional separate vessel approach at equivalent volume. It sounds like it should not work. That is exactly why it does. The two mechanisms were now individually validated. The thermal preconditioning system controlled the combustion interface. The integrated CFRP tank closed the weight equation, but validated components in isolation and validated components flying together inside a single aircraft are two entirely different engineering propositions. The problem that emerges when you run a thermal preconditioning system and a structural tank airframe simultaneously in flight is not immediately obvious from the ground test data. In isolation, each system behaves predictably. The preconditioning system draws a controlled quantity of waste heat from the exhaust cycle to manage the hydrogen phase transition. The integrated CFRP tank manages cryogenic pressure within its rated envelope. But in flight, the two systems are not isolated. They are coupled. The preconditioning system's heat draw varies with engine power setting. Engine power setting varies with flight phase, climb, cruise, descent, go-around. Every change in power setting changes the thermal energy available for preconditioning, which changes the hydrogen delivery temperature at the injector, which changes the combustion characteristics, which feeds back into the power output, which changes the structural load on the tank airframe wall, which changes the thermal boundary condition on the cryogenic side of the CFRP. The two systems do not just coexist, they talk to each other continuously through the physics of the aircraft. The old approach to managing this kind of coupled instability was conservative margin stacking. Run each system well inside its operating envelope so the interactions never reach a destabilizing amplitude. It works. It also means neither system ever operates near peak efficiency because the margins eat the performance. The AEP 100 program's engineers knew from the first integrated simulation that margin stacking would produce a flight-capable system that validated the technology without demonstrating its commercial potential. That was not acceptable as a program outcome. What AECC developed instead was a real-time hydrogen energy management architecture, an onboard control system that models the thermal state of the fuel delivery line, the structural load state of the tank wall, the combustion chamber pressure, and the propulsion demand simultaneously, running a predictive correction loop at a cycle frequency fast enough to anticipate instability before it develops rather than respond to it after it has. The system monitors over 40 sensor inputs across the fuel delivery and propulsion subsystems and adjusts fuel delivery pressure and preconditioning heat draw in real time within milliseconds to keep both subsystems operating at peak efficiency simultaneously, rather than trading one against the other. The integrated flight test data from the Zhuzhou demonstration showed fuel efficiency improvement of 11% compared to the ground test baseline, where both systems were managed sequentially rather than simultaneously. That figure came directly from AECC's post-flight engineering report. It is not a projected efficiency gain. It is a measured in-flight result. The combined architecture, preconditioning, integrated tank, real-time energy management produced a flight result that AECC's own engineering team required a second data review to confirm before releasing it publicly. Here is the honest picture. The Zhuzhou flight lasted 16 minutes. It covered 36 kilometers at 300 meters altitude. The aircraft was an unmanned cargo platform weighing 7.5 tons. Not a passenger jet, not a regional airliner, not the aircraft that will appear on a departure board at any commercial airport in the near term. The AEP-100 engine has no certified passenger service timeline. AECC has stated publicly that near-term applications will focus on unmanned cargo transport and logistics to remote or island regions, not commercial passenger aviation. The range demonstrated at Zhuzhou is a fraction of the shortest domestic Chinese passenger routes. The liquid hydrogen refueling infrastructure that supported the flight exists at one facility. These are real constraints, and they are not trivial. What the Zhuzhou flight certified, confirmed by AECC and reported by Xinhua, was the world's first successful airborne operation of a megawatt-class liquid hydrogen turboprop engine, an engine producing over 1 megawatt of shaft power from a hydrogen combustion cycle integrated with a cryogenic fuel delivery system, a structural tank airframe, and a real-time energy management architecture, all functioning simultaneously in flight for the first time. The CAAC Airworthiness Framework has not yet issued a type certificate for the AEP-100, but the flight data package submitted to CAAC following the Zhuzhou demonstration represents the first complete dataset of its kind from any hydrogen propulsion program in the world. Translate that into human scale. A 36-kilometer range at current development stage maps to early turboprop demonstrators that eventually evolved into regional aircraft covering 600 to 800 kilometers within 2 hardware generations. The routes that a scaled hydrogen turboprop would serve first, Chengdu to Chongqing, Guangzhou to Shenzhen, island logistics across the South China Sea, represent some of the highest frequency short-haul segments in Chinese domestic aviation. Zero in flight. CO2 emissions, water vapor as the only combustion byproduct. On those routes at scale, the emissions elimination is not marginal, it is total. The ground test series completed on March 29, 2026, 1 week before the Zhuzhou flight, confirmed that the AEP-100 maintained stable combustion across the full power envelope from idle to maximum rated output without a single unplanned shutdown across the entire test sequence. That is not a technology readiness level demonstration. That is an endurance result. The ceiling was not the physics. It was the integration. And the integration just flew. A flight record changes a number on a data sheet. What changes next is the question every aerospace ministry on Earth began asking on April 6, 2026. Aviation is responsible for approximately 2.5% of global CO2 emissions annually, a figure the International Civil Aviation Organization has published consistently across its environmental reports. That number understates the actual climate impact. At cruising altitude, the combination of CO2, nitrogen oxides, water vapor contrails, and cirrus cloud formation produces an effective radiative forcing contribution that ICAO's own 2022 environmental report estimated at closer to 4% of total human-induced warming. For an industry that has committed to net zero carbon by 2050 under the ICAO CORSIA framework, the gap between that commitment and the available technology has always been the defining problem. Sustainable aviation fuels reduce life cycle emissions but do not eliminate combustion. Battery electric propulsion solves the emissions equation but cannot approach the energy density required for anything beyond short ultralight flights. Hydrogen combustion in the ICAO framework has been classified as a long horizon solution, necessary eventually, available never soon enough. The regions watching the Zhuzhou result most closely are not the ones with the largest aviation industries. They are the ones with the largest unserved short-haul connectivity problems. Southeast Asia, an archipelagic region where hundreds of island communities depend on short-haul air links that are economically marginal on jet fuel economics, has the most immediate use case for a cost-competitive hydrogen turboprop. The Indian subcontinent, where regional air connectivity remains constrained by fuel cost on thin-margin routes, is a second-tier adoption candidate. China's own domestic network, with its density of short-haul segments under 500 kilometers, represents the first commercial deployment environment. What adoption actually requires is not a better engine, it is a parallel hydrogen supply infrastructure build, cryogenic storage at regional airports, liquid hydrogen production facilities within viable transport distance of those airports, and a regulatory harmonization process across ICAO member states that currently have no approved airworthiness standard for hydrogen combustion propulsion. Airbus's Zero program, targeting a hydrogen-powered commercial aircraft by 2035, has partnered with over 220 airports through its Hydrogen Hubs initiative to begin mapping that infrastructure gap. The gap it is mapping is the same one AECC just demonstrated a pathway through. In 2010, the International Energy Agency forecast that solar photovoltaic electricity would reach cost parity with conventional generation by 2050. It happened by 2015, 35 years ahead of schedule. The IEA's 2040 hydrogen aviation forecasts are now sitting on the same desk where the 2010 solar forecast sat. The competitive advantage China holds after Zhuzhou is not a patent on a hydrogen injector. It is a complete technical chain: production, storage, delivery, combustion, airframe integration, and flight certification data, built simultaneously and demonstrated together. That chain takes longer to replicate than any single component within it. The question is no longer whether hydrogen aviation is possible. The question is who builds the infrastructure that makes it inevitable. If you made it this far, you now understand more about hydrogen aviation propulsion than most people who write about it for a living. And what you understand is not just that a Chinese aircraft flew on hydrogen for 16 minutes above Zhuzhou. What you understand is what that flight actually demonstrated: that the three hardest subproblems in hydrogen propulsion, cryogenic fuel delivery, structural weight, and real-time system integration, can be solved simultaneously in a single airborne architecture by a program that built all four technical layers in parallel rather than in sequence. That is not an incremental result. That is a proof of concept for an entirely different approach to hard engineering problems. The Zhuzhou flight does not mean hydrogen-powered passenger aircraft are arriving next year. The range gap is real. The infrastructure gap is real. The certification timeline is real. What it means is that every aerospace program in the world that placed hydrogen aviation firmly beyond 2040 is now working from an assumption that a 7.5-ton cargo aircraft above central Hunan just made empirically incorrect. If this kind of story is what you come here for, the engineering underneath the headline, the system behind the record, the implication that the press release does not explain, then subscribe and hit the notification bell. That is genuinely the best way to make sure you see the next one. We're going to keep following the AEP 100 program as AECC moves toward the CAAC certification data submission, and when that story breaks, you will want to already be here. There is a real debate sitting inside the Zhuzhou result, and I want to know where you land on it. One side argues that China's hydrogen aviation lead is structural and durable because it is a systems advantage built across propulsion, airframe, fuel delivery, and certification simultaneously, and systems advantages take a decade to replicate even when the components are individually understood. The other side argues that the commercial gap, range, passenger capacity, airport infrastructure, regulatory harmonization, is still so large that Zhuzhou is a landmark laboratory result, not a market disruption, and that Airbus and the Western aerospace ecosystem have both the capital and the regulatory relationships to close that gap before hydrogen turboprops reach commercial scale. Both sides have a genuine argument. Drop your answer in the comments. I read every single one. See you in the next one.